All right. Hello, everyone. Good evening, and welcome to today's session for data analysis for biologists. So, before we begin today's sessions, does anybody have any question, any doubt? Okay. So, um, all right. Please confirm if you're able to see the screen. Are you all able to see the screen? Yeah. All right. Thank you. Okay, so here are just a few updates from the previous sessions. So we've had 3 sessions until now, and we have discussed 4 weeks. So we are halfway done with the course, right? So I hope you've all been able to submit these assignments and would continue to do so for the next 4 weeks. So today we'll be discussing the 5th week of this course, which is about correlation and linear regression. And as it was mentioned in the last session also, that in the final exam, there would not be any questions that require you the use of RStudio or any matrix calculator which are available online. Instead, these questions will test how much you've understood R and matrix calculations. So these will be simple formulas, and also the ones that we see in today's class about linear regression. Uh, if there are any questions from this topic, they would be simple calculations that you can do on pen and paper and using a simple online scientific calculator. All right. So, all right. So, right. So please, if you have any doubts with about today's session as we go through, please don't hesitate to unmute yourselves or type it in the chat box. Right. So fine. So then I'll begin. So summarizing. So a couple of weeks ago, we discussed about covariance. So whenever you have two variables, they whenever we have two variables, we can sort of check what the joint variance is. So there's a certain formula that we discussed in those sessions, and so when there are a few samples and when it's possible to calculate the mean for these samples, and you can actually do it using pen and paper. For a small sample size, you can have this this formula, and like we discussed, there has to be this correction wherein you subtract 1 from the sample size, and then you are able to calculate the covariance of these two. So there are two issues with covariance which are which sort of don't give the right indication about the relation between these two variables. One is that so covariance can be positive or negative, because as you can see here, right, we are not taking square of any numbers, right? It's just that number subtracted, subtracting it, we subtract the mean of that variable from it. So these numbers so the sum here can be either positive or negative. So even though this sign gives us the relative direction of relation of the two variables, so that one increases, the other decreases, or when one increases, the other increases, and vice versa. So this is known with the strength, that how strongly do they vary? Is it affecting it really strongly? Are we like absolutely sure that when one increases, the other also increases? So this strength cannot be exactly determined, because there's no upper or lower limit to it, right? So continuing from there, the scale at which you work, so let's say you're working on thousands, or you're working at a log scale, or you're working on centimeter versus meter, or you have different centimeter and grams. So these variables, whatever your variables are, even though the data may be the same, you have the same points, that if you plot them, they look similar. But if the scale or the values or the units are different of these variables, the covariance turns out to be different. So it's not possible to really give a strength. To give a strength, you have to have upper and lower bounds. So this problem, so if you observe the formula here, this problem is sort of alleviated when we what we do is we divide the covariance that's calculated here, we divide that covariance by sigma, right, of each of these variables. So this was the derivation that was also written in the, it was also described in the lectures. So now what happens is a positive and a negative value of rho, right here. This can tell you a positive or a negative linear relation. That's right. So so a positive relation means when one increases, the other also increases. When one decreases, the other also decreases. And a negative relation would mean that when one increases, the other decreases. So it's an opposite relation. And typically -1 and 1 are the extreme ends. So we often don't see an exact relation. So getting 1 or -1 is quite rare. But these values can vary between these two numbers, and a value of rho, or this coefficient, as they call it, the Pearson's correlation coefficient, if it's 0, that means there is no linear relation. So this is what our basis is. So we have covariance, which is an important factor, but just the fact that it was not normalized, that gave it these two problems that we discussed in the previous slide. So here we divide them, which is sort of normalizing the covariance, and then we have our Pearson's correlation coefficient. Any doubts about the Pearson correlation coefficient? So here, what these equations describe is that, as was also asked in one of these discussion forum questions, it was that there are two variables. They may be controlled. So let's take an example of two genes here. Let's say X and Y are two genes. They are expressed in some cells of our body. So when we say that maybe there's a transcription factor Z that's controlling both X and Y, controlling the expression of both of these variables. So this is our assumption that Z, that transcription factor, so P is sort of a magnitude by which Z controls X, and A is a noise. Likewise, Z also controls Y with the magnitude of Q, and B is another noise. So when you just fit in the value of, you equate value of Z from each of these equations, it turns out that Y is controlled by X with a certain ratio. So it's this ratio that we are interested in. And the noise is just what decreases. This is the noise that does not allow the Pearson correlation coefficient to be 1 or -1, because the inherent noise will always shift from a direct relation. All right. So another thing is, so here we are talking about linear relation, right? This formula, it's basically follows y is equal to mx plus c type. So when we do not have a linear relationship, but it is a monotonic relationship. So what's a monotonic relation? It means that when x increases, y increases or y decreases, but it is not linear. But nevertheless, the value doesn't keep switching. So for a few values of x, it increases, then it decreases, and so on. It's not a cyclic or a random relation. It's increasing with varying degrees of increase, or it's decreasing with various degrees of decrement, right? So what is also done here is that a lot of times it's helpful in this case to rank the data. That is, you tell, so you have values of X and you have values of Y. So you rank them. Okay, this is the highest value of X. This is the next highest value. This is the next highest value, and so on. So if you can imagine, so when you have such a, okay, let me see if I can draw this. So if here this is X and here we've got Y. So let's say it is this sort of a monotonic relation. So if you actually have, so let's say these were our data points. Right. So if you're able to rank them, so you would assume that when the rank, the X and Y variable here, if X has rank 1, then it's highly likely that Y will also have rank 1. Then the next value, X, the corresponding rank is 2. So the corresponding Y variable will also have a rank of 2. Similarly, for rank data, it is also possible to calculate another sort of correlation coefficient. So here in this case, let's say I don't exactly have a monotonic relation. So here it's only in some cases. So let's compare these 3 points. So here if I have X, so as far as X is concerned, the ranks are 1, 2, and 3, right? But when Y is concerned, out of these 3 points, maybe this is 1, this is 2, and this is 3, right? So when we talk about concordant and discordant pairs, so if you take these 2 points, they're not concordant, because in one case, because the ranks of X and Y do not follow the same way. X increases, Y decreases, but right? But right? So, but if you consider these two, then in both cases, it is then this is a concordant pair. So it all of these follow from the same idea, that you want to calculate the correlation between X and Y. These are just different ways of calculating it. So all you need to keep in mind is, when you have a linear relation, you would go for Pearson's correlation coefficient, and when it's non-linear, you can have mostly a ranked data. Then it's going to be Spearman and Kendall correlation coefficients. So another important thing to remember here is that correlation does not imply causation. There were a lot of examples described in the lectures. So this is where you need to understand the two variables that you are actually finding the correlation between. So does the correlation mean something? Does it really mean that X is controlling Y? Does it mean that there is a third variable Z which is controlling both X and Y? Or this is just by chance, right? So that's one thing. So I have a question here for you. So we would like to find these. So these are the two variables, X and Y. So I think this question was given in one of the lectures, at the end of one of the lectures. So here we have X and Y, and we would like to find the correlation between them. So we will be using R for this. So I would like somebody to tell me, how do we go about it, the exact steps, and then I would be doing these steps in R. Right? First, we plot the data. All right, so both of you have given the right answer. So to plot the data, we would have to read these in R, and I think I don't already have them written. Okay, so can one of you tell me, how do I start? I have nothing written at the moment. It's a blank R Studio console. So how do I begin with? It'll be great if you can unmute yourselves here and just walk me through, how do I write this? It's like a quick recap for R also. So I don't have the data read into R yet. You can see the environment is empty. There's no plot, nothing. We want to read the data, right? So now I don't have a CSV file for this. I just typed it into, so you can see here, this is just a table here. So I don't have it read, I think. Yeah, I have it here. Okay. No, I don't have it. These are different values. Yes, I think we can use this. Okay. So this is there, right? So this is how I'll read the data. It's here. So I am just pressing Control and Enter. So I have read these X and Y here, right? And you said that you're going to plot it. So the plot function takes in the X coordinate, X axis values first, and then the Y axis values. So these are my plot here. And right. Can you see my screen still? Yeah, I think you can. Okay. Right. So can you see this? Can you see the R Studio now? Not still. Okay, wait, let me reshare. Sorry about that. Okay, can you see the screen now? Yeah, all right, thank you. Okay, so what I did was, so we have the X values here, we read it, right? These were the 7 values, and these are the values for Y, right? And then we use this plot function here. So it first takes the X coordinate values, and then it takes the Y coordinate values, and then it just plots it here. All right. So now what do you think? Is it a linear relation? Is it a non-linear relation? What should we use? Non-linear, right? So it sort of looks like a curve can be fitted to it. So let's say we'll just try the Spearman, right? So you can see the correlation turns out to be 0.99. Likewise, so Kendall, it's also applicable for non-linear relation. It's just that the underlying algorithm to calculate the correlation is different. But as you can see, this also gives a very high correlation. Instead of, if you would not have visualized it, and if you would have just looked at the linear relation, so we would see that it's not as highly correlated, right? So it's just reiterating the fact that we should always take a look at what the data is, what it looks like. Is it a linear or a non-linear relation that we are expecting? Okay. So now that we have talked about correlation, we will focus on linear correlation mostly. So when there's a linear relation between X and Y. So what we want to do is we talk about this Y is equal to mx plus c type of relation between X and Y. And the two terms that you should keep in mind are that X, generally on the X axis, what we are is sort of our input. So when it's sort of an independent variable, you have measured it from somewhere. Rather, it's an input, or it's like a predictor that X controls Y, right? So maybe it's like you have a concentration and you observe an outcome. It's a temperature and it's controlling some phenomena. So X is called the predictor or the independent variable, and Y is the outcome of the dependent variable. These terms would be used very often. All right. So we have, let's say we have a plot. There are a lot of points. So it's not really possible to fit one line through all of the points. So we want to get the best fit line, right? And such a situation is known as an overdetermined system, because there are all these points, all these constraints. So no single line will pass through all these points. So you optimize it, and the way of optimization here is using something known as the SSR or the RSS, used interchangeably. So what happens is, so what you observed was, when you fed X1 into the equation, you got Y1. You fed X2, you got Y2. But if you have an ideal equation, if you would feed X1, what you would get is Y1 hat. So you do this for all the values of X1, you get various, you do it for all the values of Xi, that is, you get these Yi hats, you have the actual Yi's that you observe, you find the difference between them, square them. So a sum of all of these errors is what is the sum of square of residuals, right? So this difference here is your residual. You've squared it and then you've summed it. So sum of square of residuals. Now we want this difference, this value, to be minimal, because in an ideal case, when that line would actually be passing through all the points, this sum is going to be 0. So that's our ideal case. But more often than not, it is never 0 in a actual real situation. So this is how we work around with linear regression. So what we do is, the choice of M and C should be such that SSR or RSS is minimum. And through calculations at the back end, which we will not be discussing for the purpose of this course, the value of M is this. And as you can see, if you divide this by the number of samples, both the numerator and denominator, if you divide, what you would get is the covariance and the variance respectively, right? So this is the formula of M. And of course, if if you feed the mean, so the equation was y is equal to mx plus c, therefore c is equal to y minus mx. So if you feed m from the equation from the value calculated here, and you have the mean of x and the mean of y, you would get c, right? So another way of representing this is through matrices, like we do in a system of linear equations, because this is nothing but a system of linear equations. So it is y is equal to, this is, so when you multiply this, each of these become y is equal to mx plus c, right? This is how you multiply the matrices. You can check that the dimensions of this matrix, this is n cross 2, and this is 2 cross 1. So the outcome is going to be n cross 1, right? So it satisfies the minimal requirement for matrix multiplication also. And if you rearrange them, because you want to find out what m is, the internally, this is what calculation happens, but we do not need to worry about this because mostly we'll be using R to calculate these values. So once you have actually calculated these values, we need to check if they're actually correct, right? So there are a few diagnostic checks that need to be done. So there are 3 things which should be checked. So this was the model we started with, and RSS is what we calculated, right? So in case there is no linear regression, that means x and y are independent. So y is going to be a constant, right? It's going to be a horizontal line. And for making the model a good fit, like as in it should be at least realistic, what we say is that the value of y, so the y-intercept in this case is going to be the mean of y. So in this case, the total sum of, so we similarly, instead of y hat, actually we use the mean of y. So this square is going to be, the sum of squares is going to be TSS, or total sum of squares. And R square is nothing, but it's actually giving you a difference between RSS and TSS. So here what we can see is that if RSS is actually equal to TSS, then it means that this value becomes 1. So R square becomes 0. That means it's absolutely a bad fit. And if RSS is 0, as we wanted in the ideal condition, then R square is 1. Right? So again, it is very rare that you would be checking 2 independent variables or 2 perfectly fitting variables. So the value of R square generally varies between 0 and 1. The second test is the 2 estimates that we got, which were M and C. Were they a good estimate from the sample for the population also? You had some samples, like in the previous case, we just had 7 data points. So if we calculate, so in that case, anyway, it was not a linear relation, but had it been a linear relation, is that also a good fit when we have more data from the population? So this, if you remember from the previous lectures, this uses t-statistics, right? So which here we are using the sample statistic, subtracting the population statistic and dividing by the standard error in our sample. The standard error in the sample is what we can calculate. So we calculate this for both our variables, right? M and C, or in this case, B and A. And then we calculate the probability that the observed t-statistic, is it greater than this or not? So we get a p-value, which is the value of probability. So if that probability is less than 0.05, we can reject the null hypothesis. We accept the alternate hypothesis that actually, yes, we can, these observations are significant. They're not equal to 0. So the way we have to go with this is, these regression coefficients, M and C or A and B that we calculate, if any of them are non-significant, that means the model that we started with, they were wrong, right? We miscalculated R square, right? So we need to recalculate R square, and we'll again recalculate our regression coefficient. To correct the significant coefficient, we recalculate this. And sorry, this should be R square. So we would likely be observing an improved value of R square, all right? And the third diagnostic check is our confidence interval. So this is just to give you an estimate that the values that you have calculated, how much can they vary for 95% of our values, right? So for 95% of the sample, for 95% of our population actually, so like we discussed, for population it's beta. So for 95% of population points, it's going to be around B. It may not be exactly B. So what that B is, so have we correctly assumed B or not? So that estimate for the 95% is what our confidence interval is. So for both alpha and beta, we calculate using A and B and the T statistic respectively, right? Typically, it's calculated for a 95% confidence. So this value of A that we fit in our T statistic is going to be 0.05. So mostly, so these underlying formulas you should know, but most of these calculations would be done using R. All right. So before we go to multiple linear regression, right. So we will quickly take a look at a few of these things using R. In the meantime, if you have any question, please let me know. Today's session might not take us a complete 2 hours. So if there are any other doubts from any of the previous sessions, or if you want to just learn R a little more, we can do that. Okay, you can also open RStudio in your systems and do it alongside. And if you want, you can share your screen later in the session. And if you get stuck anywhere, we can have a troubleshooting session also. Right? Yes, absolutely. The confidence interval can be anything other than 95%. So 95% is generally assumed so that most of your data points, right, a very high number of your data points are falling within that range. All right. Yeah. Okay. So we look at one of the most commonly used data sets that we've also used previously, the IRIS data set. Right. This is what it looks like. So, so do you assume any of these? Okay. So now before we start, just a quick recap about something in R. I want to check what is the data type of this table. What do I do? How do I check that? Class. Good. So class and bracket, I read it as I. So, right. So it's a data frame. Now, I also want to look at what is the data type of each of these columns. So some of these are numbers, some of these are alphabets. So how do I check that? Right. So one of the ways could be that you do str, str bracket, and you write the name of the data frame here. So you can check, it gives you the data type of each of these columns. So the first 4 columns are numbers and the last one as a factor structure. Yes. So the function name is str, right? So yeah, all right. So factors, so any type of data frame, any type of data type, especially characters, they're generally converted into factors when you have a limited number of types. So here there are only 3 levels, 3 types of species in this data set. All right. So now I want to calculate the correlation, right? Just a correlation between any 2 of these columns. So can anybody tell me how do I do it, and tell me what the exact command should be? You can type in that command, and I want to calculate the correlation between any 2 of the features. So as in I want all versus all. Core command. What should I write inside the core command? So let's assume it's a linear relation for the time being. So I understand. So we'll be using Pearson's method. Yeah. Or Iris. Okay, so let's see if this works. I, right? I read it as I. So now it says error in core I, must be numeric. So this is an error. And one fundamental part about using R is to be able to understand what the error is. So can anybody tell me what the error means and why has this error come and how do we correct it? Right, so it says X must be numeric. So X is what our argument has been, what we gave it inside for. So we gave it I. So this is what I was. This is what I looks like. You can see it here also. You can see it here as well. So it says that X must be numeric. Good. So now what we want is we do not want to find a correlation between this column and anything else, right? So what we are going to do is we just want to find the correlation between the first 4 columns with each other. So instead of I, now we'll be working with I. So if you remember, before the comma comes all the rows and after comma comes the columns that we want. So here I want the first 4 columns. So this becomes my data frame of interest, the data that I want to feed the core. So now it's run without any error. So here 2 things are important, 3 things rather. So it's a square matrix, all versus all. So we had 4 columns. So this output here also has 4 columns and 4 rows. All the diagonals that you see here is 1 because X versus X, Y versus Y, they of course have a 100% correlation, positive correlation, right? They don't follow an opposite trend. And it's a symmetric matrix because the correlation of X with Y is the same as the correlation of Y with X, right? So here there is no directionality. So it's a symmetric matrix. So you see sepal width with sepal length, it's minus 0.11. Likewise, if you look here, sepal width with sepal length, here it's also minus 0.11. So this is how you'll be running the core function. Now here I did not specify any method, right? The next argument here. So like one of the next things I can specify here is the argument, right? The method argument. So I did not give it Pearson, Spearman, Kendall, anything. So what do you think it calculated? Did it take any one of these randomly? It calculated what did it do? It took Pearson's, right? So this is something known as a default value. So a lot of functions in R, you would have seen, they have a default value because a lot of times you don't need to, because mostly this is used for linear relations. So it was decided that Pearson's correlation would be like the default. And if you want to change that, then only you need to specify. But it's always good to specify if you are unsure about what the defaults are, so that there is no incorrect calculations done, right? So another way, in case you just want to find between any 2 values, so instead of a data frame, you actually just have one pair that you want to test, so you can have the methods specified separately, right? So that's good. So okay, so with that we're done with correlation. Now we discussed linear regression. So this is again one of the data sets that Sir talked about in the lectures. So we want to say if age can be a predictor of systolic blood pressure. Now, first of all, tell me which will be our X here and which will be the Y. Rather, tell me which will be the independent variable and which will be the dependent variable, or like the predictor in the outcome, and why. Like, yeah, it's so this is the first important thing, because in case of correlation, it was not important to determine the direction, because their directionality or X versus Y versus S does not make a difference. So, but obviously you realize that if you interchange X and Y, the slope and the value of the intercept changes, because then you're looking at it from a different perspective, right? Systolic is a dependent variable on X, right? Because our argument is that age may control systolic blood pressure. Okay. So the first step is to visualize that should we even go for linear regression on this? So we plot this. So you can see here that yes, it looks like there is some sort of a linear relation. You can fit some sort of a line here. The next thing is, okay, so let's actually take a look at the Pearson's correlation coefficient. So the X value here is age, Y systolic blood pressure, method Pearson. So we see that, okay, there's a weak correlation, but a correlation nevertheless. So we can form linear regression and we can find the value of X, M and C here. So this is one important feature to remember. So you see, when you look at the plot function, the first argument is X, the second argument is Y. In core also recommended is the first argument is X, second argument is Y. In case of linear regression, when we use the LM function, the way it's written is Y tilde X. So when you have so it's just an easy way to remember is when you have a comma separating X and Y, you write X comma Y. And when it's a tilde, which means you are sort of giving a formula, it's Y tilde X. And so here in case of, so another difference you may see here is here we give it the data frame dollar column name. And in this case, we give column name tilde another column name, and we give the name of the data frame as the next argument itself, right? So we perform this and we save the value into any variable, reg in this case, and we take a look at what reg looks like. So there are a lot of things you can understand from this. So what we take a look at first is R square, which is the coefficient of determination, right? So R square, remember, it was 1 minus RSS upon TSS. So you can see here RSS is 0.43, which is okayish value. And then you can see the significance here. So we want to find the significance for both our variables, right? For age in this case, it means age was X. So M here means, so age value here means it's going to be our slope. And the other thing is the intercept. So you see here that we have values for this. Estimate means the actual value, which is so M here is 0.97 and C here is 98.71, and they're both significant, right? And yeah, so we see that it's significant and we don't need to recalculate these values because both of them turn out to be significant. And finally, we also take a look at the confidence interval for both of them. So the function is conf int. We feed in the calculated regression model and we give it 0.95. So it means the least 2.5% and 97.5% would lie between these values. So the actual value was 98.7, minimum can be 78 to 119 and so on. All right. And now let's actually plot the line here. So one of the important features, so the function here is abline. So one of the important features of abline is that a plot must already be present. It cannot plot the points because you're not giving it X and Y themselves. What you're giving it that to just plot the line using the output from, so reg is nothing but the output from LM. So abline is able to just print the output of LM onto an existing plot, right? So let's say if I would have deleted this plot here, if I just run this, it says that error, new plot has not been called yet. So what I do first, I plot this and then I write this. So a line is fitted, right? Another example. So this was just like we discussed, you have different concentrations and you calculate their absorbance. So same way, we plot x comma y. This is what it comes out. It looks like a linear relation, right? So we also calculate the correlation between these two, which is, it's a very high correlation. We find out the linear regression model. This is y delta x. And we take a look at the summary. So if you remember from the Beer-Lambert's law, the intercept should be 0. And because you remember that, right, you can actually see that the concentration and absorbance are 0 at this point, right? So the intercept is not significant, so we need to recalculate. The argument we took here was incorrect. So here we implicitly specify that there is no intercept. C is 0. So we recalculate, we again find the summary. So now what you can see here, so in this case, you check the concentration. So the value initially was 0.0147, right? And now you check the value has changed. And another thing to check here is this thing, R squared. So initially we took, it was a wrong assumption, right? That it follows mx plus c, with c not being equal to 0. So the R square in that case was 0.9838. It is a very good number, no doubt. But now see, it's increased to 0.9879. So the R square is also improved because actually you have now taken a better fitting model. So like in the previous case, we'll be plotting both the lines. So let's take a look at both the lines actually here. So the one in blue is the correct line out of RL2, right, with the correct assumption. And if we would have taken the previous one, so you see it has a non-zero intercept. And visually, you may not be able to distinguish between these two. But of course, you can check that the R square is now improved. It means that RSS has also decreased. So definitely the blue line, the blue line here is a better fit, right? So any doubts until here? We are done with the first part of today's class. We'll quickly go through multiple linear regression also. Just a few steps different from simple linear regression, right? So, yeah. Let me know if there are any doubts. Because if you're not asking any questions, I can assume either everything is clear or nothing is clear. So please let me know if everything is clear indeed. Clear? All right, good. Okay, fine. So multiple linear regression. So now it means that until now we were talking about one determinant of a variable of an outcome, right? So there's only one variable which predicts the outcome, but an outcome can be dependent on multiple predictors. So systolic blood pressure, for example, it does not necessarily only depend on age, but maybe it also depends on some other features. Okay, let's say it depends on what climate you are staying at. So we don't know if they make sense, but it could be dependent on a lot of features. And this is what you would like to find out through your studies. So each of these, so what it means is that the outcome, y, it depends on x1, let's say variable type 1, x2 is another variable, xk is another variable. And these b1, b2, bk, they are the respective weights, and a's are intercept. All right. So now an important part about this is, so which we will come towards in the upcoming slides, is that these features themselves should not be related to each other, because then it sort of introduces an error. We say that y depends on x1, y depends on x2 also, but internally actually x1 is controlling x2 or vice versa. So you would be so it's like an incorrect assumption. right? So it's very important that x1 and x2 do not affect each other. So this is what is known as multicollinearity, as you would have seen in the lectures. But anyway, we'll come towards it. So here, it's just now it's now a larger matrix. So you have the first kind of variable, let's say age. You have some different values you determined, right? Different inputs. Let's say this was temperature, another set of values, some other feature, whatever it is, x3 and so on. You have k variables. Corresponding to each of them, you have the value of the outcome. And normally, the data points that you have should be more than the number of predictors, right? And so again, you can have the same kind of matrix, y is equal to xb in this case, same way. So here what you need to remember is that the number of rows, it's n, right? The number of columns is k plus 1, because this 1 corresponds to this a here, this intercept term, right? So k plus 1 rows in this case, k plus 1 columns in this case, these matrices can be multiplied and you would get your outcome y. Okay, so there are the same 3 diagnostic checks that should be done, but there are just a few differences in this. Coefficient of determination, we know it's 1 minus RSS by TSS, right? But what happens is, as k increases, as you fit the data more and more, it is possible that RSS, by its innate formula, it decreases. So just by definition, R square would increase. So you would say, oh, it's actually a good model, but when it was not a good model. So we just want to say that if the predictors increase, you should sort of penalize R square and decrease it a bit. So when you have increased and decreased it, so right? So it's right. So sorry, right? So this formula right here. So if you fit in k is equal to 1, as it was the case in case of simple linear regression, so it becomes n minus 1 upon n minus 1. Right, sorry, n minus 2, right? So it does not make a lot of difference in that case. Although it is recommended that once you, so if you remember from the formula that we saw in R, even for a simple linear regression, it calculates adjusted R square. But it should not be used because there it does not make sense. There, this is the only formula. But when k increases, then it becomes necessary to use this formula. So in that case, we would not be focusing on the normal R square, but we instead be using adjusted R square, right? Which is represented by R square by. And the statistical test of significance, one thing that you need to check is, of course, t-test for each of our variables here, right? All b until a. But another thing also needs to be checked for the whole model, right? So here we only take a look at the coefficients of each of our inputs, right? Each of our predictors. So that is beta 1, beta 2 until beta k. So the alternate hypothesis is that at least one of these betas is going to be non-zero, right? So anyway, this is the internal formula of F0. This is for your reference. And right, so you remember what yi hat and y bar indicate, right? I hope this is clear. And so this is what we discussed, that these x themselves should be independent of each other. So we talked that n should be much, much greater than k. So in that case, when we talk about the rank of this matrix, it's equal to the number of the least of the two. So here we talk about columns. So we have k plus 1 columns. So if each of these columns are independent to each other, then the rank is going to be k plus 1. So in case these columns are not independent, then what happens? The rank reduces. It's not k plus 1 anymore. So if you remember from this formula here, for this X matrix, we also need to multiply X transpose with X and find its inverse. So when you multiply X transpose with X, it again becomes a, so it becomes a k plus 1 times k plus 1 matrix. and it should also have a rank k+1. But if its rank is not k+1, it's not a full rank matrix, then that becomes non-invertible. So you would not be able to calculate the system of equations. Another way in which this can become, so one thing is that X is a predictor, as in X is like a linear relation of X2 and Xk maybe, or so on. Another way in which it becomes a non-full rank matrix or a rank deficient matrix is, let's say if one of these variables are not well dispersed, right? So if all of them have a value of 10, 10, 10, 11, mostly around 10, then that can actually be written as a form of this last column. So that should also be ensured that none of the variables that you see, they are actually like a constant. So it's very important to choose what these variables are. So two things should be kept in mind, that these variables, they should be independent of each other, and these variables should be well dispersed. That is, they should not have a constant value for all the measurements. All right. So, right. So what can be done to avoid such a thing is, so let's say k is equal to 3. So you have 3, so x1, x2, and x3. So what you can do is you can check Pearson's correlation coefficient pairwise. So x1 and x2, you write cor x1, x2 method is equal to Pearson, then cor x2, x3 method is equal to Pearson, and cor x1, x3 method is equal to Pearson. So these Pearson's coefficient, correlation coefficient should be really low, because we should not be expecting a linear relation. But this is okay to do if you're assuming that x1 controls x2 or vice versa. But what if x1 is a linear combination of x2 and x3, right? So let's say x1 is actually equal to 2 times x2 plus 3 times x3. So in that case, this first method will not be sufficient. So in that case, what is recommended is doing something like a VIF. So what it does is, for x1, it calculates if it can be represented as say like a linear combination of all the other variables, right? So you see, let's say xj here in this case is xi. So you calculate if it can be expressed as combination of x2, x3, and so on, but all except x1, right? So, and you calculate r square for it, and then the corresponding VIF is going to be 1 upon 1 minus r square. So VIF greater than 10, right? So a high value of VIF, which means this is really low, which means r square is close to 1. So when VIF is a really high number, generally said more than 10, then it means that that column may be actually represented as a linear combination of some other columns. So it's a good way to actually, it will be recommended to actually remove that from our matrix to begin with. So we don't add that, right? So this is there. We quickly go through a few examples in R. Any doubts until now? So this was another data frame that we looked at in the lectures. So here it's the length of the fish, the temperature, the age. So we just want to see if the length can actually be represented as a linear combination of age and temperature and maybe another variable. So, okay, so in this case, the constant is actually assumed to be 0. So there's no intercept in this case, because age 0, temperature 0, there should not be length of, like the fish should not be alive. So this is our model, right? So we can just take a look at this regression, and we take a look at the summary here. Just a second, right? So both age and temperature, they look good, right? They're significant. We have these estimates for them. Now, in this case, you would like to look at the adjusted R square because you're doing a multiple linear regression, right? You can also take a look at the F statistic, the corresponding p-value, that is also good. So that means we can now continue with this we can also likewise find the confidence interval. So, so like in the previous case, we saw we can plot this. So, but that would not be possible for a, like you can't plot all the categories at the same time. You can at most have a 2D graph here. So, but nevertheless, um, normally that's not a required practice either. So another example that was seen was this. So there are all of these M, P, R, and S, 4 different variables. Here it was said that S is our outcome variable. So S should be expressed as a combination of M, P, and R. So we can actually plot them one by one to see if there is actually a linear relation. So here I would like you to take a look at this and tell me if the slope, that is the corresponding coefficient with, so here we are plotting M and S. S is our outcome variable. So in this case, the slope is positive or negative. Slope is negative, right? Right, negative. And then in this case, what do you think? Is there a slope? Does it look positive, negative? So it looks weakly negative, right? It looks like this sort of a line can be fitted, right? So this also looks negative. And this is the last one here. What do you think this looks like? It is dispersed, so does not look like a very strong correlation, but I think this looks more positive. So let's see if this is actually the case, right? Okay. So we can take a look at correlation in this case. So the diagonal, that's 1 always. It's a symmetric square matrix, understood? So now you can see here that if you take a look at S versus M, that's negative. So that's what we saw here, right? So slope, and so this is correlation, but that's also giving you an estimate of the relation between the two, right? M and P here, that's also negative. So you can see it's weakly negative, right? It's very close to 0 because there's a very high dispersion along, like if you have a horizontal line that can fit. So the slope is not going to be a very strong slope. That's same as the case with R also, right? So we can see here it was weakly negative and this was also weakly positive, right? Okay. So now we want to calculate the linear regression model, the exact values of these slopes, right? So, so there are 2 ways. So in this case, we can either specify what we exactly want, right? Or we can just put a dot. So it means from the M data frame, S column is my outcome and everything else become the inputs, become the predictors, right? So each of these 2 mean the same thing, right? Which means that here we have not assumed the final intercept, the final, like that to be non-zero. We have not assumed that. So either of these will give the same output. So we take a look at this, and here you can see all of these things are significant, right? And the adjusted R square is also a good value. P value is also significant here. So this looks good, but just for the sake of completion, we would like to check the variance inflation factors to actually understand if M and P and R are not themselves linear with each other. So here you need to use the car package. So this is how you would install. You can also go into tools and install packages, or you can simply type install.packages bracket and write car within double quotes. You would need internet connection when you are installing packages. This step needs to be done just once. And every time you open RStudio, you just need to call this library using library bracket car. The function here is VIF. Here also the input is going to be this output of LM function. So you write VIF bracket R square. Sorry, I did not run this step. So it just says loading the required package. VIF, this is the output. So it's recommended that if VIF is greater than 10, only then does it make sense to ignore um, any of these parameters, right? So that is what I have here. I have a few practice questions for all of you. So please be active, participate in this. I think there are 5 or 6 questions. So here you want to calculate the Pearson's correlation coefficient between X and Y. You have these data points. So what formula would you use for this? Do you remember what formula we have to calculate Pearson's correlation coefficient?
Rho equal to covariance of X and Y divided by standard deviation of X and Y.
Right. Good. So now here, do we really need to use the formula? Can you think of a relation between X and Y here? Does it look like there's some trend?
Seems linearly dependent.
Right. So X is exactly the double of Y, right? So if you plot this, so it's going to follow a linear relation, an exact linear relation, right? Y is equal to 2x. So the Pearson's correlation coefficient in this case is going to be 1. Because X is increasing, Y is also increasing. It's an exact relation. There's no noise. Remember, we discussed a few of these examples here. I think this was first thing here, right? Well, so Y is equal to something into X plus noise. When noise is 0 and the coefficient before X is a positive value, then it means it's a perfect positive linear association. So it's rho equal to 1, right? So this is one of the trick questions. So whenever there's a formula required, you should always take a step back and see if there's something special about the data that's been given to you. You can always calculate it. Of course, you would reach the same answer, but this question here does not require you to calculate anything, right? So the answer is 1. All right. So which of the following values of coefficient of determination indicates a good fit of a linear equation to a data? First of all, how do we also know coefficient of determination as? What is the another symbol that we use for coefficient of determination? Sorry. R squared, right? So now remember, R square varies from where to where. What was the formula of R square? Where does it vary from? And then think of which of the answers is correct. Right? So R square varies from 0 to 1, right? So so it's 1 minus RSS by TSS. So it can never be negative. So this option goes away. Whereas instead, if you were actually talking about the correlation coefficient, so in that case, it can be both -1 also and +1 also. So there, a linear data can be both positive linear and negative linear. So in that case, if it was something in that direction, then -0.99 is a better linear relation than any other value here. But R square cannot be negative, so this goes. Now you have these values. So good fit means a higher value between 0 and 1. So yes, C is the answer here. Good. Now, third question is that there's an experimental data and we hypothesize that the growth of pea seedling, it depends on 2 features, the salinity of the soil and the moisture content. And we want to find the linear regression. So we want to find the linear regression, perform linear regression to find the relation between the growth of the seedling and these 2 factors. And we'll be using linear algebra. We'll be making that matrix. So you have the coefficient vector, right? You remember y is equal to xm or xb. So these coefficient vector, how many elements are going to be there? And additionally, so yeah. So how many vectors, how many elements are going to be there in that vector? And can you just tell me what the elements are? First of all, how many elements would be there in the coefficient vector? 2. What would be those coefficients be? Like, can you just explain? So let's say the formula is, so can you, before that, can you, sorry, tell me what the formula is. How do we write it? Y, right? Y is equal to, so y here is growth of pea seedling. Let's say it's the length or the height of the seedling. That is equal to, yeah. So can you just tell me what the equation here it's going to be? How do we write y is equal to mx plus c? Y is equal to something else?
We go with quadratic equation.
Quadratic. Y is equal to ax square plus bx plus c. Can you just type it out? Y is equal to what? You can take any variables and just explain what. So let's say the two variables are x1 and x2. So how do we write? You can just type it in the chat box. Any idea? We've seen a lot of these equations in this session. So we have y is equal to a plus bx. Now we have 2x actually here, right? So we have x1 and we also have x2. So x1 and x2 are what we are. So we are measuring 3 things in an experiment, right? We are measuring the soil salinity. Let's say we write it as x1. We are measuring the moisture content. Let's say it's x2. We are also measuring the height of the pea seedling. That becomes our y. So now we assume that x1 and x2, they are both affecting y. When two things are affecting something, we would have like a coefficient that how strongly is it affecting, how strongly it influences. So there's going to be a coefficient here. So let's say we just call it A, right? Whatever you, so maybe we'll call it A1, right? And correct. And let's say this here can be A2, right? But you remember there is another feature here. Because whenever there's a linear regression, we can always, we should ideally always have a constant term here. So let's say it's going to be P, right? Is that clear? Oh, sorry. Just a second, I'll just share my screen again. Please think about it in the meantime. Right? So, just a second. Share. Yeah. Okay. Right? So, whenever you are making that matrix now, right? So, the coefficient matrix is going to look like A1, right? A2 and B. Later on, B can turn out to be 0. That's absolutely okay. But initially, this coefficient vector would be, it would have 3 elements. All right. Now, the next question is, which of the following is used to measure the goodness of fit? So, how would you rate that the multiple linear regression that you did, how good it was? C. So, coefficient of determination is R square, right? So, but that is not sufficient when you are doing multiple linear regression. You need to use R square bar, right? Okay. Next question is, which of the following functions will be used to perform linear regression bar? You just used it. So it's the LM function. So I think this is the last question. So what is the minimum value of variance inflation factor that is used to calculate while calculating multicollinearity? So if you want a hint, we can just quickly go to this here, right? So, right. So R square can be anything between 0 and 1. So ideally, it would not be 1 because then VIF would go to infinity. So if you want to calculate the least value of VIF, so you can backtrace. Least VIF means this needs to be the largest, right? So when would this be the largest? When this is equal to 1, right? So when R square is 0 and there's no relation, then the denominator becomes 1. Therefore, VIF becomes also 1, right? So VIF can never be less than 1, right? Because the denominator is never going to be greater than 1. I hope that's clear, right? So I think with that, we come to the end of today's session. It was a relatively shorter session. But since we have time, if there are absolutely any doubts, especially about using R and RStudio, then I would be happy to clarify those. Right, so the session is being recorded. It would be uploaded to YouTube with the other previous sessions. The deadline for this week's assignment is day after tomorrow, Wednesday, 1st March. And our next session will be next Monday. So, yeah. Please let me know if there are any concerns, any clarifications required. Right? Is everything clear to all of you? So if you've missed any assignment, so if you remember from the calculations for this course, I think the best 6 assignments are going to be taken out of 8, right? So if you've missed one, I think that should be fine. Out of the rest of the 7, rest of the assignments, the best 6 would be taken, right? So I think that should not be a problem, right? Yeah, and yeah, so I hope you're liking the course and you're able to understand it, right? These simple topics that we are covering here, they become really handy once you pursue this field in depth, right? So yeah, sorry. So if you have any doubt, then you can post your questions on the discussion forum, right? I can also answer any of your questions there. Yeah. So, all right. Right. So, okay. Keep learning. We will meet again next week. All right. Thank you so much for attending today's session. Bye-bye.